Okay, here we go. Let's really get rolling on this. Put everything away, please. I want to see. We got a lot of stuff to do in a few days. So everybody, face front. Look up here. Get your notes out. Let's do this quickly. Here's kind of the plan. I'll give you just a little background as to what we're doing here. So the next module or next unit we're moving into, both modules have to do with polynomials, and so it's really short. We're going to zip through this pretty fast. But one of the things that we're going to be doing pretty quickly is we're going to be multiplying and dividing and adding and subtracting polynomials, which is not hard stuff, but it does depend on knowing your properties of exponents. Now this is something that you would have gone through in Algebra 1, but everybody's coming in with a little different Algebra 1 background, and so I want to make sure that everybody's on top of these skills. It's not even, this is just assumed in our book. There aren't even any problems to practice this. So I want to make sure, I'm going to add some stuff. I've got a couple practice assignments up, just to give you a chance to kind of get back up to speed with this. So let's go through these properties of exponents. Okay, so first of all, in this, and I'll put this PowerPoint online too, so you can download this or look at it at home if you want to study, so you have some materials because the book's not available for this. A and B are going to be the bases of the exponents, and we're just assuming those are real numbers. The exponents are the bases of the powers. The exponents are going to be the m's and the n's. And for now, we're just going to assume that those are integers, right? Although later in the class, all the stuff we're learning now, those will work for fractional exponents too. But we won't mess with that for now. What's an integer? What's an integer? What kind of number? That's important. That's a really important word in math. That's something before we do anything else. You got to make sure that you know what that means. What's an integer? Give me an example of an integer. Take a guess. Yes, ma'am. -3. Give me another one. Perfect. That works. What's another one? -5. Yeah. Give me another one that's maybe just a little different. Okay, sure, but how about
8?
Positive 8. Okay, good. Now give me another one that's different than both of those. 0. Okay, give me one that's not an integer. 7 is an integer. 3/4 is not an integer. What's another one that's not an integer? 2i, not an integer. What else? Say it again. 1/2 is not an integer. Something that's maybe not a fraction. Fractions evidently are not integers, right? Well, I shouldn't say that. Like 8/4 is really equal to 2, so that is an integer, right?
Or decimals?
Decimals are not either. So like 0.37, not an integer. Okay. How about pi? Nope. Square root of 2? No. Okay. So what do you think integers are then? Okay, they're positive and negative whole numbers is one way to think about it. Here's the way I like to think about integers, and you take it or leave it, but this is kind of how I think about it. If you make a number line, and that's 0, what's that going to be? What's that going to be? What's that going to be? Etc. Every dash you would make on the infinite number line would represent an integer. Okay? They're all good. Does that make sense? Okay. So that's what we're dealing with. Those are the exponents. All right, so first one. The product property. I don't care if you know the names of these at all. I don't remember the names of them. It's not important. Just know what they mean. This is saying, what does that mean? A to the m. If I look at a to the m, this is, thank you. Whoops. This is what we call, that whole thing is called a power. Right? You've heard that before. What do we call this part right there? Do you remember? Let's start here. This is easier. What's that? What's that thing that's raised up there like that? Well, the power really means the whole thing. It's an exponent. Yeah. This is an exponent. And what do we call that thing down there that's on the bottom? It's typically a number, but it could be a variable. Could be a real number. It's what we call the base. An exponent is always comprised of a base taken to an exponent, raised to an exponent. Okay? So for example, if I said 2 cubed, what's the base? Good. 2 is the base. What's the exponent? 3. Okay, and the power is 2 cubed. What if I said x to the 7th? What's the base? What's the exponent? 7. Good. Okay, so then when we talk about something like this, we're saying if we have a product of like bases, what do we mean by that if we say like bases? The same number is in the bottom of the power, right? So in this case, it's a both times. If I have a to the m times a to the n, if I multiply like bases, what do you do to the exponents? Add them up, right? So a to the m times a to the n is the same thing as saying a to the power of m plus n, right? Okay, make sense? You're familiar with that one, right? Seen that one before? That'd be like saying, what if I had x squared times x cubed? That's equal to x to the 5th, right? I add when I'm multiplying like bases, okay? Okay, now what if I take a power to a power? So I'm taking a power to an exponent. What do I do then? Multiply the exponents. So for example, if I have something like x cubed squared, that's the same as x to the 6th. See, that's different, right? Okay. Questions? Okay, what if we take a power of a product? So this is saying if I have, notice the parentheses, these are important. If I have the quantity a times b to the m, then what this tells me is I can break that apart. Effectively, I could distribute the exponent to both of the bases, right? So for example, if I have something, I'm going to give you 2 examples here. What if I had something like x times y cubed? How else could I write that? Yeah, I could distribute the 3, the power of 3 to both parts, and I could write that as x cubed, y cubed. Okay, what if I had something like the quantity 2x cubed? How could I simplify that?
2 cubed.
Okay, good. That's going to be the same as 2 cubed times x cubed. And what's 2 cubed? That's a number, so I can simplify that. 8. 2 times 2 times 2, right? So I'd write that as 8x cubed. Okay? Make sense? Okay, now I'm going to tell you something that you can't do, because sometimes it's a real common thing that people in Algebra 2, they make this assumption that if you can do this, well then you probably could do this also. You probably could say a plus b to the m equals a to the m plus b to the m. Is that true? No, that is not true. Not true. How come? Think what a plus b to the m really means. That means that base of a plus b times itself m times, right? So it's going to look like a plus b times a plus b times a plus b m times. That's going to be a tremendous mess, right? When I expand all that out, it's going to be a huge string. That's much more complicated, right? This is simple. All you do is just distribute the exponent. But when you've got a sum or difference, a plus b or a minus b to a power, you can't do anything easy with that at all, right? That is simplified. Okay, make sense? So if I gave you x plus 3 to the 4th, is there anything we can do simple with that?
Yeah.
What?
X to the 4th.
No, you can't, because they're being added, right? So I can't do that. What I would have to do, and we're not ready for this, this comes later on in the unit, what I would have to do is multiply x plus 3 times x plus 3 times x plus 3 times x plus 3. That's a long process. I'm going to show you a shortcut for that, but it's a full day of just talking about just that alone, right? So for now, there's nothing we can do with that, okay? Make sense? That's an important one to remember. All right. Okay, the same things that we can do, oh, actually, here's a different one. Okay, the negative exponent property. This is another one that's kind of an important one. In fact, I'm gonna do this one separately. So this tells us really two things. If we have some base a to the negative m, what it tells us is it's equal to 1 over a to the m. Okay? But there's another part of this. It also means this. 1 over a to the negative m equals a to the positive m. So here's how you got to think about this one. Now listen very carefully on this and write this in your notes, and this will make this a simple deal. Here's what I always tell people with exponents, with negative exponents. Whenever you see a negative exponent, immediately you trade it for a positive exponent in the other side of the fraction, right? So for example, when I say side, I mean numerator versus denominator, top versus bottom. So if there is a negative exponent in the top, that just becomes a positive exponent in the bottom, okay? If I have a negative exponent on the bottom, that's the same thing as moving it to the top and making it positive, right? So simplify then, what's this going to be? What's x to the minus 3? Yeah, that's the same as 1 over x to the positive 3, right? What is 1 over 2 to the negative 3? That's move the 2 to the top and make it 2 to the positive 3, which is what? 8. Okay, make sense? Okay, what if I did, and I'm going to really throw a tricky one at you. What if I said this? What if I said 2x to the negative 2? What's that going to do?
2 squared x squared under 1.
Okay, there's a couple different ways I could go with this. To me, the first thing I would do is I'd say, okay, I see that negative exponent, so I'm going to write this as 1 over whatever the base is. Don't change it. Whatever the base is to the positive exponent. So it's 1 over the quantity 2x squared, and now I can deal with the 2x squared. What am I going to do with that?
1 over 4x.
Okay, good. I'm going to distribute, aren't I? Star keeps changing. I don't know why. Right there. I'm going to take that 2 and just distribute it to both parts, right? So I'm going to get 1 over 2 squared times x squared. And what's 2 squared? 4. Good. So I'm going to get 1 over 4x squared. In the Moodle assignment, let's put phones away. Please put that phone away. I'm going to ask you to always write your answers in terms of positive exponents, right? So we want to write it with, you're going to have to put that x on the bottom, okay? Does that make sense? Okay? All right. How about 0 exponent property, the easiest one? Anything except 0. Any number taken to the 0 power is always equal to what? 1. No matter what. Any number to the 0 power is always equal to 1, except 0 itself. 0 to the 0 doesn't make sense. That's what we call an indeterminate form. That one wouldn't work. But anything else, any other number to an exponent of 0, regardless of what it is. It could be I. It could be, well, actually, we're going to do real numbers. It could be pi. It could be a googol, which is 10 to the 100. It doesn't matter. Any number, regardless of how big or small, positive or negative, taken to the 0 power is always equal to 1. Okay, quotient of powers. This is one I want you to think about as being similar to the product property, right? So if we do a product of powers, if we multiply like bases, we add exponents, right? What if we divide like bases? What are we going to do? Subtract. Okay, here's why. Here's why. This is really just a combination of two things that we just talked about. It really helps to think about it this way. This is, I know, I promise you, today's going to end up being really helpful to you because you're going to do a lot of this stuff, and it puts it. I think when you link them together like this, it just gets a lot easier to do the algebra of exponents. In my opinion, the algebra of exponents is easy. It's really simple stuff, but people get confused by it because sometimes I think they just have never had a complete picture of how they all work together. But you're going to find this stuff not very difficult compared to some stuff we've done. So if we're doing something like a to the m over a to the n, let's do this in 2 steps. How could I write that as a product? How could I write this bottom power on the top? A positive exponent on the bottom would be the same as what on the top? Negative, right? Does that make sense? Everybody get that? Because that's the only difference between a positive and a negative exponent is it just switches which part of the fraction you're in. So I could write that as a to the m times a to the minus n, right? Everybody see that? Positive exponent on the bottom is the same as negative exponent on the top and vice versa, right? So now that that's a product, what did we say we do when we multiply like bases? What do we do to the exponents? You add them, right? When you multiply like bases, you add the exponents. So this is equal to a to the m plus negative n, right? Which is the same thing as a to the m minus n. So we can just skip the middleman here, and we can just say when we divide like bases, we just subtract exponents, right? Okay, but there's one other thing that none of the books tell you that I'm going to tell you that's really helpful. What if we had to do something like this, and we want to write this in terms of positive exponents? What's x to the 10th divided by x to the 7th? Now what do I do if I divide like bases? I subtract, right? So it's going to be x to the 10 minus 7, which is x cubed, right? Does that make sense? Okay, but what if I reverse that? What if I had something like x to the 8, let's do it this way, x cubed over x to the 8. Okay, so that's the same as x to the 3 minus 8, which is x to the minus 5. But then I got to write it in terms of positive exponents, so I got to add one extra step. What's that going to be? Put it on the bottom. Good. So negative on top is positive on the bottom, right? But look at this. I want to show you a better trick here. Here's the trick. We can change this rule. Yes, we know that this is true. A to the m over a to the n equals a to the m minus n. But it's also equal to 1 over a to the n minus m. Now, why would you do that? Well, what about this case? What if the bottom exponent is bigger? I could just keep this on the bottom and subtract 3 from 8. And that's a shortcut. You see that? So here's how I always say this rule. I always say this rule, if you divide like exponents, you keep, like bases, you keep the base where it has the most power and subtract the other exponent, right? So in this case, we would say 8 is more powerful than 3, so we keep the x on the bottom and subtract 3 from 8. See what I'm saying? Okay, to me, that's a really helpful way to think about this. It makes the algebra quicker, simpler, okay? Okay, and then the last one, the power of a quotient. So this is really similar to the power of a product. It's the same rule applies. If I am multiplying 2 bases and I take that to a power, I can distribute the power, right? Same thing is true for division. If I'm dividing two numbers, or whatever, 2 bases, it could be exponents, and I'm taking that to an exponent, I can also distribute. The only times I cannot is when I'm adding or subtracting. Multiplying and dividing both work. Okay, so for example, what if I had something like x over y to the 5th? How could I write that? Exactly. I could, because they're being divided, because they're not being added or subtracted, I could distribute the exponent and write that as x to the 5th over y to the 5th. Okay, what about this one? What if I had 2 over x cubed?
8 over x cubed.
Okay, I'm going to get 2 cubed over x cubed, and 2 cubed is a number. What's that?
8.
Okay. Make sense? Let's look at just a couple quick examples. How am I gonna deal with that? What's gonna be, Greg, what's gonna be the property I'm gonna use there? I'm multiplying -5 to some power times -5 to some power. So the bases are the same. If I multiply like bases, both -5, what do I do to the exponents? Multiply like bases, you add them, right? So I'm gonna get -5 to the 4 plus 5, right? -5 to the 9, which is just some big number, that number, okay? How about this? Do I have like bases?
Yeah.
I do. So if I multiply like bases, Tanner, what am I gonna get here?
X to the 7.
That's it. X to the 5 plus 2, X to the 7. Okay? Do you see that the variables are easier? Because variables, you don't have to just, X to the 7th, you don't have to do anything with that. That's the answer, right? It's easier to deal with variables than it is numbers here, which is kind of the opposite of what you think. So what's this gonna be? Reese, what do I got here? A power to a power. Multiply. Good. So I'm going to get 2 to the 3 times 4, 2 to the 12th, which is 64 squared, which is 496. Okay. How about this? 3 to the 8th. Big number. Okay. Okay. How about this one? -6, I'm multiplying, so I add them, right? Yeah, so -5 to the -6 plus 4, but what's -6 plus 4? -2. So what do I gotta do now? Victoria, what am I gonna do to that? If I have a negative exponent on the top, what do I do? 1 over -5 to the 2. Good. And what is -5 squared? Positive 25. Good. Okay. How about this? Brandon, what's that going to be? I'm dividing like bases, so what do I do there? Subtract. So x to the, 5 minus 3, right? X squared. That's it. Okay, what about this? What am I going to do here? What do you think? Trevor? If I've got, there's a couple of different things you could do first. What if I deal with this, as I say I've got a quotient, I've got something divided by something, all taken to the 2 power. What can I do with that 2? I can distribute, right? So I can distribute it to both parts. On the top, it's going to give me an r squared. On the bottom, I'm going to get s to the -5 to the 2. Colby, what do I do with that? If I take a power to a power, what do I do? Multiply it. So I get s to the -10 on the bottom. In Savannah, what's the last part of this? If I've got a negative exponent on the bottom, what do I do?
The 1?
Well, I'm gonna remember, negative on the bottom becomes positive where? On top. Yeah, that's what I think you're saying. Good. So it's gonna be r squared times s to the 10. That's our answer, right? Okay. What about this one? Yikes. What am I going to do there? Haley, what am I going to do there? Let's start with this guy over here. I've got, looks like a product of 2 things to the power of 2. So what can I do with that? Multiply. Good. So I'm going to distribute, right? And then, so I'm going to go like that, right? So the first step is going to be, I get 7 squared times b to the, and I should have parentheses around this. They should be like that. B to the -3 to the 2. Well, if I take b to the -3 to the +2, what's that going to be? What am I going to get from that? What do you think? What do I do if I take a power to a power? Gabe? Multiply. Okay. So I'm going to get 7 squared is 49. B to the -6 times b to the 5 times b to the what? 1, right? If I don't have an exponent there, there's an implied 1. And now look at this. I've got 3 bases multiplied together. b to the negative 6 times b to the 5 times b to the 1. What do you suppose I do if I multiply three bases together? Add them up, right? If I multiply like bases, I add the exponents. That works for more than 2 at a time. So negative 6 plus 5 plus 1 is what? 0. Okay, what's b to the 0? 1. Anything to the 0 is 1. So the answer is 49. Okay? I think this is the last one. Yep.
I have a question. Can
Yeah.
you do the last one?
Yeah.
What happened to the one? What happened to the one?
To the 1? Well, because what is this one right here, you mean?
No. B to the 0.
Oh, yeah, so that's the same thing as 49 times 1. And what's 49 times 1? 49. Okay. Okay. How about this one? What do you think? Brooke, what can I do with this? This is a little bit trickier. There's a couple things I could do, but see if you guys remember the shortcut. If I divide like bases where the bottom is a bigger exponent, do you remember our shortcut? Say it again. It's going to be 1 over. Good. So we're going to keep it on the bottom. We keep, oops. So we, oh my gosh, are you kidding me? We're not going to do scientific notation. Okay, so I keep the base on the bottom, and how do I subtract? So what minus what?
10.
Yeah, you get that? What's our rule? When we divide like bases, we keep the base with the biggest exponent and subtract the other exponent, right? So we keep it on the bottom and write it as 1 over x to the 10 minus 5, which is 1 over x to the 5th, right? Make sense? Questions? Okay, that's it. That's our review. The rest of it's just stuff we're not going to take care of right now. All right, so you may grab a Chrome.